So the second fundamental theorem of calculus says if we have a function that is an integral function, g of x equals the integral of from a to x of f of t dt. That's an integral function because it's a function that has an integral in it. And we go and we take the derivative of that. Well, it just counteracts each other, basically. So that means this. If this is g of x, then the derivative of g of x is d dx of the integral, which ends up just being the function with x, our variable up top here, in place of t. This t is called a dummy variable because when we take the derivative, that t just goes away. Okay, and it's replaced with this x. A is a constant here. So it basically just tells us that the derivative is the opposite of the integral, and it reverses it in a way. So let's try this. Let's take this function g of x here, and let's go ahead. It's an integral function. Let's evaluate the integral. So the antiderivative is t cubed times 2 minus 2 squared, and we're going to evaluate that from 2 to x. And if we plug in x first, we get 2x cubed minus x squared, and then minus, and plug in 2 times 2 cubed minus 2 squared. And this is just going to come out to be 12. So this whole thing simplifies to 2x cubed minus x squared minus 12. All right. So there's our function, g of x. So we took the integral, we got this. Now, let's see what happens when we take the derivative. G prime of x is the derivative of 2x cubed minus x squared minus 12. Well, using our power rule for derivatives, that just goes to 6x squared minus 2x. And the 12 is going to go away, right? Because the derivative of 12 is 0. So look what happened here, all right? We had a function defined by the integral. We evaluated the integral, and then we took the derivative, and look where we ended up. 6x squared minus 2x. Well, where did we start? 6t squared minus 2t. So we did all that work, and we just went forwards and backwards, kind of, and we end up with just 6x squared minus 2x. Well, that's what the second theorem, fundamental theorem of calculus, is telling us. If you take the derivative of an integral function, well, we're just going to end up with the function itself as a function of x, the variable here. So here we have a function that we don't exactly know how to find the integral of right now. This, by the way, can be written as, there's like an invisible 1 there. And so this can just be written as 1 over 1 plus t. And we can move the dt out a bit. That might be make a little more sense to you there. Well, we have the integral of this function here, dt. So we want to go ahead and find the derivative of that. Well, according to FTC2, all we need to do is replace that t with an x. And we're done. Seems like it's too easy, but that's all there is to it. We're taking the derivative of an integral, and they reverse each other there. And this constant, it really doesn't matter what it is, because when we took the derivative, this constant went away. So this could be a 2 or 2,000 or 2 million. It's just going to end up with a constant, and when we take the derivative, that constant goes away, and so it doesn't matter what it is. We just need a variable on top. So now, what happens when we have a more complex function here? So we have the integral from 0 to x squared plus 3. So we have a little more complex situation here because that's not just a simple x. So we can't really use the fundamental theorem of calculus yet. But what we're going to do is this. And we're going to say, let u equal x squared plus 3. All right, if that's the case, then this integral becomes the integral from 0 to u of sine of the natural log of t plus 7 dt. Now you should be looking at that and saying, oh my goodness, I can't take the integral of that. I don't know how to do that yet. I may never know how to do that. I don't know. Well, we're in luck because we're not really trying to evaluate f of x. We want f prime of x. Now, f prime of x is df dx. All right, well, we've just changed it from x to u. So we're going to have to use the chain rule here, and we're going to need to find df, whoops, can't write. How about df du times du dx? So that's our chain rule there. And we can see the canceling that goes on here. So let's see if we can do that. Well, here we have the function f defined not in terms of x, but in terms of u now. And so we can say this is, the derivative of that is going to just be, according to FTC2, sine of the natural log of u plus 7. That's that, using FTC2 now. And we got to multiply by du dx. Well, what is du dx? Let's come over here, and we can find that fairly easily. Du dx is the derivative of this with respect to x. It's just 2x. So times 2x. Now, we don't want to leave it this way because we still have a u in here. So we got to go one step further here. And we'll see that simply it becomes the sine of the natural log of u. What was u? Let's go back here. U was x squared plus 3. X squared plus, so we're going to put x squared plus 3 in place of the u. X squared plus 3 plus 7 times 2x. And we can go ahead and clean this up and write this as plus 10 in the middle. And that is our answer. So what happened? Well, before, when we had just a plain old x, we just dropped the x down in here. Well, we almost did the same thing. We're going to take this expression and put it in place of t there. And that's where we got our x squared plus 10. Okay, but we need to also multiply it by the derivative of this du dx. So we'll need to multiply by that. So what we can do from now on is we can just jump straight from the original problem here. Jump straight from here. We can skip all this u business, and we can jump straight to the final answer here, maybe after a little bit of simplifying there. Okay, so this is what we get when we plug x squared plus 3 in there. It becomes x squared plus 10 inside the parentheses. And du dx on times the outside. Maybe we'll put that 2x in the front sometimes, but that's it. All right? So there you have it, okay? Here's a quick proof of the second fundamental theorem of calculus. I'll let you think through that a bit there. Not going to spend time. It's not important to memorize there. The idea is just that the derivative of an integral function is the function itself on the inside. So we'll leave it at that. I hope that helps. You can work on the first page of the assignment there. We'll talk a little bit together about the displacement problems on the back, but you can work up through problem 89. Thanks a lot, guys. Keep working hard.